Okay, so this is lesson 12.4, graphing logarithms and evaluating their inverses. A couple lessons ago in 12.1, we discovered how to graph an exponential equation in the first place. So I want to do a quick refresher of that. When we did an exponential equation, you had a base to an exponent. The most basic base would be base 2. That modeled an exponential growth, where from left to right you had a steady, there it goes, and then a skyrocket. So you had a gradual increase and then it shot up really quickly. So I want you to notice that this one has a horizontal asymptote at the x-axis at y equals 0. We're going to compare that today with logarithmic graphs. See, remember, logarithms are exponents. It's a different way of writing the equation in the first place in order to solve for that missing exponent. That's what a logarithm is, an exponent. So I want you to notice a couple of things. In the last lesson, in 12.3, we talked about how exponential form a base to an exponent equals an answer, BIA. We also talked about how logarithmic form is BE, base B of the answer equals the exponent. So when you first notice converting from exponential to logarithmic form, y equals 2 to the x, the base is 2. Remember, exponential is BIA. The x is the exponent, and y is the answer. Well, when you convert that to logarithmic form, the base is 2. Log is BE, so the answer is y, and that equals the exponent of x. See, the most basic logarithm, though, because it's a function, check it out, it has y equals, not x equals. The x and y are switched. In the very beginning of the year, one of the first units of the year, I think it was unit 2, we talked about what happens when you switch x and y. That concept was about inverses. What I'm trying to tell you right now is that this is going to be really interesting. I know the bases are the same, though they both have a base of 2. But exponentials and logarithms graph as inverses. Now here's what I mean. Let's just see what happens. If this is the most basic logarithmic graph, y equals log base 2 of x is how you say that. Remember, log is BE. So this is a base. That's a funny looking B. Log is BE. Base, answer, and it equals an exponent. If you change that to BIA, the base to the exponent is y, and that equals the answer, that's x. So making a table of values, pretty easy. When you plug in those x's, though, you kind of have to work it backwards. Here's what's interesting. With logarithms, it's actually easier to pick y's, plug them in, and get x's. You can totally do the normal thing of inputting an x and outputting a y. But since logarithms graph as inverses, it's actually easier, believe it or not, to pick a y. Think about this. If you had picked a y of 0, 2 to the 0 is what x is. Well, when the exponent is 0, the answer is 1. So when x is 1, y is 0. If I had picked the x and wrote it like that, 2 to the what equals 1, I have to work it backwards. Now, hopefully clearly, it makes sense that 0 has to be y, because the only way to get a base to become a 1 would be when the exponent is 0. So you have a choice. You can plug in your x's where they go and figure out what the y is, or you can pick y's, plug them in, and get x's, which is actually easier. Now, since we set up with x's for some reason, I don't know what I was thinking, we're going to finish it. So if x is 2, which is 2 to the first, what is y? Hopefully it's clear that for 2 to stay the same, y needs to be 1. Now what about when x is 4? Well, 2 squared is 4, so y must be 2. And here's another one. What about when x is 1/2? How do you send a base across the line and change its sign? Well, obviously not a sign change, but I meant for the exponent. So hopefully you're catching on. Hopefully you recognize that that's going to have to be -1, because 2 to the negative first, in fact, does send the base across the line and changes the sign from a negative exponent to a positive one. So that was kind of working backwards, because we had to kind of think of what y needed to be to make that true when we picked those certain x's. Regardless of how we get there, once you make the table, plot and see what happens. I want you to notice our original parent function of an exponent went through 0, 1. For a logarithm, it goes through 1, 0. Again, they're inverses. You switch the x and the y. 2, 1. This was 1, 2. 4, 2. This was 2, 4. If I had picked another one, I would have picked 8. Reason? Because 2 to the third gives me 8, and that would have been 8, 3, which just so happens to be the inverse of 3, 8. 1/2 -1 is right here. If I would have picked 1/4, it would have been -2. It's getting infinitely closer to that asymptote. This is what's interesting as well, and hopefully it makes logical sense. If your exponential had a horizontal asymptote, your logarithm instead has a vertical one. So we have a vertical asymptote. Again, we've switched x and y, so the asymptote had to switch as well. And then our graph from left to right grows like this. Now, another interesting tidbit for you to understand. This base is 2. The base is 2 for this basic logarithm. When we did exponentials back in 12.1, any base greater than 1 was considered a growth, and any base caught in between 0 and 1 was a decay. Well, this base of 2 is greater than 1. From left to right, is this graph growing? I'm going to go with yes. It's definitely growing. What's our domain? When we did exponentials, our domain was all real numbers left to right, and our range was the asymptote of 0 to infinity. Since x and y have switched, because they're inverses, and domain and range have switched as well then, because they're x and y, our domain is actually the vertical asymptote to infinity, and the range is all real numbers. We switched them. Boom. X and y switched places. Now, they graph as inverses. Make sure I clarify that. Our vertical asymptote, not horizontal, because again, that's opposite. We've switched them, would be a vertical line at the y-axis. The y-axis is the equation x = 0. Okay, that's a lot of writing. Hopefully that wasn't too overwhelming. Now, here's what I want also to connect. This is like the most basic parent function of all the logarithms, the basic base of b, of 2. Well, if we're here on the next example, you can use your transformations and just shift them. If you know what your original looks like, then shift it. Now I'm going to change colors so you can kind of see the difference. Sure. It should not be a shock or a surprise that because that's inside with the x, that 3, we go opposite of our instincts. We're going to go left 3. The 1 is outside, being added, up 1. So we're going to take that same parent function and we're just going to go left 3 up 1. Now I could certainly change to that form and I could fill out a whole brand new table, but why would I do that when I know transformations and I know that this parent is really easy to plot? So let's graph it. If I had started at 1, 0 right here, instead I'm going to go left 3 up 1. Left 1, 2, 3 up 1. If I had gone for the point 2, 1, left 1, so right here, left 1, 2, 3 up 1. If I had done 4, 2, left 1, 2, 3 up 1. If I had done 8, 3, left 1, 2, 3 up 1. And if I had done, let's see, 1/2 -1, which is right there, left 1, 2, 3 up 1, puts it right there. Think this through. Your vertical asymptote just got shifted left 3. So your vertical asymptote is at -3. With exponentials, your horizontal asymptote depended on anything being added or subtracted on the outside, moving it up or down. But since we're dealing with a graph that's an inverse, it's not up and down that matters. It's left and right that matters. So there's a vertical asymptote at -3. And we connect our dots from left to right. There it goes. It's the purple graph parent, the parent function, base of 2, shifted left 3 and up 1. Our domain is now dependent on the vertical asymptote's placement. So that would be -3 to infinity. I want you to understand that that has a parentheses because, of course, a vertical asymptote can't be touched, so it wouldn't get bracketed. And our range, low to high on the y, is all real numbers. It goes down forever and up forever.